So thanks so much for coming here today. Today we're going to talk about Pokemon, and in the meantime also learn maybe a little bit about MLOps. So quick show of hands, who here has played Pokemon? Ah, great, that's almost everyone in the room. Just for the few of you who may not know, in Pokemon it's an RPG, it's a game. You pitch your own monsters against other monsters, other Pokemon, in battle, and try to fight till they faint or death or whatever you may play. And the very basics of this game are the Pokemon types. So you have a bunch of Pokemon, each of one has a type, or maybe two. So for example, grass can be super effective against water, water can be super effective against fire, and fire against grass again. And if you want to be any good at playing Pokemon, you need to at the very least know all of these types. Problem is, there's a few more than just the 3 of them. There's about 18 of them, each with interactions between them. And there are also a lot of Pokemon. Back when I was a kid in the 90s, there used to be 150, or 151 to be precise. And right now we're kind of at a problematic over 1,000. So at that point, it just becomes way too much to learn them all by heart. I don't have the time to go through all of those 1,000 Pokemon and learn their type or their 2 types. What I do have the time for is to over-engineer a machine learning model and learn them for me. So that's what we'll be doing today. Just a quick bit of background. I'm Rob. I'm from Utrecht in the Netherlands. I currently work as developer advocate at Iterative, and I'm very much a water Pokemon type trainer. And in a short while, I'll discuss why I chose water, at least for this presentation. So the agenda for today, we'll create a classifier. We'll then introduce DVC and show why and how we're going to use it, and then a little bit of a demo to show how it actually works. Creating a classifier. Well, what do you do if you want to create a classifier? In this case, we start with scraping the images. So we want to get all of the Pokemon images from the Pokemon website so that we know which ones to classify. Then we create a very basic convolutional neural network. Or in my case, you get your girlfriend to do it for you because she's better at this stuff than I am. Shout out to Alma. And then we start predicting which of these Pokemon, the sprites we just scraped, is actually a water type. So why did I pick water? Class imbalance. With only 1,000 Pokemon, it's a bit difficult to predict all of the classes for all of the Pokemon. They're by far the most water Pokemon, so it becomes easier for the data science project. So, as a data scientist, I usually tend to start out with a notebook. I just pull up Jupyter Notebook, type in some code, start mucking about, and see where we end up. So let's do that. This is what the notebook looked like once I had a working prototype. So we start with some imports, some parameters for setting. This is some maintenance. We pre-process some data to get the image, the Pokemon labels. So this is one hot coded. Each Pokemon, which types do they have? Then we process the scraped image data that we got earlier. And you can see that here in the data frame as well, because they now have an image path, which you can put into the model. And at the end of the entire notebook, we can put in an image, this Mudkip. He is actually a water Pokemon. Our model will provide a prediction. So 0.87, that's probably a water Pokemon, and indeed, Mudkip is a water Pokemon. For those who are very familiar with Pokemon, I think it's also a ground Pokemon, or maybe only its evolution is a ground Pokemon. Okay, so our model is working perfectly here. Very happy about that. And as you can see, we can pull up a confusion matrix. We've got a few false positives, a few false negatives, but by and large, our model is doing pretty good. So we're finally ready to play some Pokemon, right? No. Because a new Pokemon game just got announced. It was released last month, I think to mixed reviews, if I'm putting it nicely. But Pokemon Scarlet and Violet got introduced. And now our entire data set, which we use to train the model, it's outdated. So what can that entail? Well, we're getting a new data set with new Pokemon, with new image sprites. That might introduce some drift in our models. It may affect our performance, we don't know that yet. And we may even need to retrain our model. Sounds familiar yet? Hopefully, yeah. As data scientists, the work we do is never stagnant. We can create a model and we can put it into production, and a week from now the entire world may change. I think we saw it with all the predictive models. When COVID struck, stuff changes. The world around us changes and we need to adapt. So I think in an earlier talk we saw the XKCD comic, where you just start shuffling your pile of data until the right results start coming out. With a little bit of a nicer word, I'd like to call it experimentation. That's a process we have to adapt to the changing world. But the problem with experimentation, at least if you start doing it in a notebook, is that it's very hard to keep track of which stuff you're experimenting with. So we may change the input data we use to train the model. We can change some hyperparameters and parameters, some class weights maybe. We may even be interested in becoming a different kind of trainer for this presentation. And all of this stuff gets real mucky real fast. So another show of hands. Who here has experimented and kept track of their input settings by writing on a piece of paper, or if you're very advanced, by writing an Excel sheet? Yeah. Notepad, oh, also good. So if I speak for myself, this always goes awfully awful. It gets mucky. Another thing we can change. So just by that, we multiplied our number of experiments by 5. It becomes difficult to track. And soon, if you're trying to reconstruct a model, to reconstruct an experiment, it becomes a game of who's that Pokémon, or what is that model? What were the parameters we chose? What were the data we put into it? What were the code as it was at that point? What was the resulting model? The artifacts it produced, the plots. All of it is separated, and you can't find all of this together anymore. So we're going there. You don't, or you're no longer able to reproduce your model. And if we want to properly experiment, if we want to run those experiments and be able to revert to them, we need to go for full reproducibility. Now, for code, if you've got a software engineering background, you may know that this is a solved problem, right? You just use Git, you use Git repo, you go to GitHub, GitLab if you're using it, and you can look up the entire history of your code. But we can't do this for datasets. We can't do this for model files. They're too large to be important. So what if we could get that very nice Git-based approach, but use it for our datasets and for our models? And for that, we want to capture each experiment as the combination of 3 separate things. The data that went into model training, the code that we use to model train, and the parameters at a given point in time. And we can do that. We use Git for the code and for the parameters, everything that's text-based, and we use DVC. And this is where I launch into a sales pitch. So the full disclosure is I work for Iterative, as you saw earlier. Iterative creates DVC. The good news is I'm not trying to sell you anything because DVC is free and open source to use. So I already discussed a little bit the why for DVC. We want to be able to track and version our experiments, and for that we need to also track and version our larger data sets, our models, alongside Git. Now let's see how DVC can help us do that. DVC consists of 3 major components: data version control, its namesake, the pipelines that we use for our model training, and experiment tracking. If we start with the first one, that's probably the one the most of you will know if you have heard of used DVC in the past. We have a Git repo. This is what it may look like. So we start at the bottom, and you've got your commits, all successful order. We've got a branch here. And in a branch, we have a given data set of Pokémon. So these are the Pokémon sprites that we are using. But we can't necessarily store those sprites in the Git repo because they're image files. So what do? We get DVC. We run DVC init. And DVC replaces the image files themselves with a metadata file. And that metadata file is text-based, so it can easily be tracked by Git. Then we have the DVC cache, which does include your images again. They're physical images on your hard drive. And DVC knows how to tie the metadata files to those locations in your DVC cache. And the great thing about this is that DVC doesn't duplicate your data. So for example, if we have a new commit, which you can see here because we changed the typeface, something has changed. our data set has changed here as well, because now we're using Charizard instead of Omastar in this new data set. And DVC doesn't duplicate the other two that are still in there, so Slowbro and Victory Bell, Weeping Bell, what's his name again? So straight away, we have a DVC cache. We don't need to duplicate our data for multiple experiments, and we can track given data sets to given experiments in our Git commit history. And if you want to get really fancy, just like you usually don't run Git only on your local computer, you can also mirror your DVC cache to someone else's PC, which may be an S3 bucket or something on Azure, can even be Google Drive. We can upload this to the cloud. So that's the basic data versioning. Then we can take it up a notch and go for pipelines. So this may seem familiar if you know DAGs, directed acyclical graphs. You have one thing, and it's once the first stage has completed, we go to the next one. And we don't. It's a one-way street. We only go one way. So this reflects the notebook I showed earlier. We first have a data pre-processing stage. We then have the data loading stage. We then do some model training, and finally we start predicting or evaluating. And each of these stages produces outputs. So, for example, the pre-processing stage, in this case, we get a data set with labels and a data set with images. And that's all nice and good. So we have the outputs tracked. But then those outputs are also inputs for the next stages. So the data load stage will only kick off once DVC detects that the data set labels and the data set images has been generated. With that pipeline, let me show it one more time, we can now run our entire notebook, or rather the code that we copied from our notebook into our Python modules, and make sure that we get everything reproducible. Not only the code, not only the parameters, but our data and resulting models as well. And now we can finally start experimenting or the messing about in the pile of data until we get the results that we want. So what does that look like? This is our pipeline again. So in the middle we have our pipeline. We have defined that as code in the dvc.yaml file. I will show this a little bit later. And our inputs are the code, the data, and the parameters. And the outputs that this process produces are model, plots, and metrics, plus any other artifacts that you may generate if you so choose. And we can define one pipeline run of this. We can version each of these components with either Git or with DVC. So generally, you'd go for Git for text-based files, and if it's something larger like an image data set, you probably want to go for DVC. And each of these pipeline runs corresponds with a Git commit, or an experiment in this case. And the good thing, or the nice thing about this is that at any point we want, we can go back to another commit, as you can see there up top, and just do git checkout, then DVC checkout, and you get that very experiment that we ran earlier. A while back at a conference, I was talking to a German guy, and he used to work for a bank, and he was asked, hey, we saw this very funny thing going on. So do you remember that one model that we built 5 years ago? Yeah, there's some unexpected results, and we now need you to find out which data went into training it, which data was used in prediction, why it's making these kinds of predictions that we don't really want. Yeah, also we need it fast. They spent about 2 weeks trying to reproduce that model with an entire team. And in certain fields, this auditability is kind of important. So you can save a lot of time simply by tracking everything in a Git-based approach, and then being able to do Git checkout and DVC checkout in this case. So let's zoom out to the real world for a little bit, because thus far I've been talking about Pokémon. It was nice to get you into the room, but usually we don't get to play around with Pokémon for our talks. Or for our talks, I can do whatever I want, but as a data scientist working in a grown-up field or in a grown-up profession, you usually are worried about healthcare or about finance or infrastructure. So this approach that I just described, how is it interesting to us as professionals, as data scientists? Well, as I mentioned, in healthcare, you may be interested in knowing which patient data went into training, what kind of model. And it may be very important to be able to reproduce precisely that experiment. Same goes for finance. You want to know why someone got a loan, or I used to work for a fraud detection team, why someone's order was marked as possibly fraudulent. So that traceability and auditability is a key concept of this philosophy. And then also collaboration. can be very important. I don't know if you've ever collaborated in a data science team. It's very easy to get something working on your environment, on your computer, and then move it over to a colleague of yours or their laptop. And as soon as you try to run it, you get a bunch of errors and dependencies missing. Bundling all of this together and saying, just give me that commit, allows for effective collaboration. That's the philosophy behind this Git-based approach to data science and experimentation. Now let's see how that actually works in practice. This is where I'm taking you out of notebooks for a little bit, because a lot of this is what we define as code. And we generally do so in YAML files. So here you can see my IDE. I'm using VS Code. And I have split up the notebook and the stages we defined earlier, which you would just run subsequently, into separate Python modules. It's just copy-paste work and append a .py at the end of the file name. And from there on out, you can run these from your command line, and it produces outputs. So for example, the train.py here, this is precisely the stuff I also had in my notebook. I copy-pasted it here, and at the end, we save the estimator that we train. And then in the DVC.yaml file, we define these modules as stages in our pipeline. So for example, this is just the command that we execute. This can be anything that you want, as long as it would run in your CLI. We define outputs, dependencies, and parameters. And the params are defined in your params.yaml file, where they're automatically detected. So for example, here I changed the number of epochs to do a new experiment and the batch size. And for good measure, also the learning rate. I'm just messing about here. And with one single command, we can kick off the entire pipeline, run a new experiment, and see how the results hold up. So if you look here, it scrolls by a little fast, but the first two stages, they didn't change. So it might as well skip them. I mean, we have cached the output. We can just reuse whatever we had going on. Because if you're not using your, or changing your input data, then you're also not wanting to rerun the first few stages. We do our model training. It takes a little while, so might as well grab a sip of water. And in the end, we end up with a new experiment that we can evaluate. So how do we evaluate these models? We can run this from our CLI and show the experiment table that DVC provides. We can also, let's see what we get here. Yeah, we can also use the DVC extension for Visual Studio Code, which provides a nice graphical interface for this. So here you see a bunch of experiments, each with changing parameters, and among these, the experiment that I just ran with update accuracy. And then you can see the top one there, it performs quite well. We're quite happy with the results. So from there on out, we can take this experiment and create a new branch from it, which will automatically be incorporated into your Git repo. Here's where I run a new experiment. So for example, this generation, I'm interested in becoming a dragon trainer. And in this case, the first few stages do change. So now it needs to do the data preprocessing again. And in the end, it will also end up there for comparison and to see which one of these experiments work nicely. So to provide a little bit of recap, I see I'm doing good in time. We train a model to predict whether a given Pokémon or a Pokémon sprite was a water type Pokémon. So for example, Mudkip is indeed a water Pokémon. And we had an experimentation-based approach to that. We want to keep messing about and we want to keep track of our experiments so that we don't end up with sticky notes and Excel sheets and the need to reproduce something 4 years down the line. Just now earlier I was in a talk about code archaeology. We kind of want to prevent that if we can. And DVC and Git provide a good approach for that. Because as the world changes, so should our models, so should the stuff that we do with the data that changes as a result of the ever-evolving world around us. And those model changes, we achieve that through experimentation, the messing about in the pile of data and hoping the right stuff comes out. If we ever want to do experimentation in a proper way, we need our experiments to be reproducible. And for that, that's where this entire bundling comes together. And that's something we can't just do with Git. We need another tool for that, and that's DVC. At least that's what I'm proposing you use as a tool for that. All of this together takes us away as data scientists, maybe the alchemists of yore, when we're just messing about and not documenting our results and our findings, and then taking those findings that we have, properly documenting them, or ensuring that other people can take those findings and continue our work for us, and also making sure that we can always get back to something that we did a few commits ago. Thank you for your attention. If you are interested in learning more, I do have a few further resources. The project I just described is available as a GitHub repo. I also have a blog post. All of this is on iterative.ai, where I take the original prototype in a Jupyter notebook, then wrap that notebook so that you can execute it from your CLI and use that as an experiment tracking or experimentation platform. And a follow-up post will take that approach and also properly split up the entire notebook so that we have the stages separately defined. We're also at the booth, so come chat us up if you're interested about learning more. And some acknowledgement, which you will be able to find in the slate later on. Thank you.
Now for some questions. Any questions on the...
Are you sure?
Ready? Nice catch.
There we go.
Okay, first of all, thank you for your presentation. It was very interesting. I have a question. How easy it is to scale it to a Kubernetes cluster or AWS to train a lot of models on a lot of GPUs?
Right. So the DVC part that doesn't actually do your model training for you. It defines a pipeline and it executes commands. We do have other tools in our ecosystem, so I don't want to devolve into a sales pitch, but Iterative provides a number of open source tools that together allow you to do your MLOps. And another of our products, CML, would definitely help you do that. That's basically CI/CD for your machine learning. So you can use your GitHub Actions, for example, to run a script every time a new merge comes in or a commit or every other Tuesday of the month, and then provision whatever cloud instance you want and do your model training for you. We can talk about that a little bit later if you want.
Okay, thanks.
Can I just ask you for 1 second?
Sorry.
So, if you have a question, Rob is going to throw you a pair of gloves.
Oh, I'm doing it.
Yes.
Oh, you didn't mention
So,
that.
better come up with some if you want some nice gloves from Iterative.
Yeah. Yeah, they were supposed to be in the goodie bags, but they only arrived just now. So I don't... okay, pass it on if you want.
Any other questions for Rob?
Yeah.
If you will help with this, thanks.
I'm going for the gloves. My question is, what is the difference between this framework and using Git LFS for storing your data sets?
Yeah, that's a question I get a lot. So Git LFS has some downsides with regards to caching, I think. I haven't used LFS extensively in the past. For one, LFS doesn't provide the experimentation and the pipelining functions. And it's also a little bit more restrictive with regards to what you can put in it, if I recall correctly. Yeah, come chat us up at the booth and we can dive into this further. I've got a few colleagues who are more proficient at it than I am.
Great. Any other questions?
Yes, right here.
Over here? Or?
It's going to be there first.
Oh, over there.
Got it.
Hello. Is my understanding correct that if you want to store data set attached to an experiment, it's going to be a Git commit?
Sorry, come again? If you
So
want to store
every experiment for which you want to store the data for, is that going to be a Git commit?
So what you Git commit is the metadata file that DVC creates for you.
Yeah.
And the data itself, that's what you can put in whatever you're using for your storage.
Yes.
Okay.
So, however, we would do hundreds of experiments while training a model. So, I would have hundreds of Git commits, like one per experiment?
Yeah, so in the background, each experiment is sort of a commit, but not really. I think that there's a technical term for them. And you can promote them to true commits. And then create a branch from there, or just commit them to your development branch that you're already working on. But you don't need to keep track of each and every experiment you run.
Okay, thanks.
Jill had a question? Here we go.
Thanks for the talk. You showed the visualization tool for VS Code. If you significantly change the parameters that you feed into the model, maybe you change from a neural network to XGBoost or something like that, how does that show up in the visualization? Is it all fine? Because it looked quite tabular.
Right, I don't think I can easily show it here, but you have a drop-down where you can select which columns you want to show up. So if those change for an experiment or for a new branch, for example, you can disable them or re-enable them. And they can show up empty as well if they don't have the right data there. I think you also saw that in this instance.
Anyone else?
I see one in the front row. All right.
Hi.
Hi.
A small question about the cache. Did I get this correctly, that the files in the cache are stored with something like an MD5 hash or something as a file name, like a hash as a file name?
Yeah, MD5 in this case, although I think that's up for debate currently somewhere in the ticket.
Okay.
Yeah, so you've got an image, Pokémon sprite, it generates a hash, and that hash is reflected in the metadata file that Git stores for you.
Okay, and my question is, have you heard of, or are you aware, or is there an official IPFS connector for the cache?
I'm not sure, to be honest.
Okay.
Again, we can discuss that with Yuri, maybe.
Cool, let's chat later. Thanks.
We have question in the front row.
Let's quiet it down a little bit more with the gloves being unpacked.
Yeah.
Everyone has gloves now, by the way? Hands up if you don't. Okay.
Put up your cold, empty hand.
Great talk. I have a highly technical question for you.
Oh dear, sorry, is it so late already? Yeah.
Do you like mudkips?
Honestly, I pitched that I was a water type trainer. I've been a fire type trainer since my youth. So the first, I'm very sorry to disappoint you. Charmander, yeah. I think the first game I played was actually Pokémon Sapphire, so that was Torchic for me.
Okay.
Yeah.
Okay. I can.
We're
I can live
down
with
here.
that.
Any other questions?
Over there. Yeah. Oh, there we go.
Go.
All right, so thanks for the talk. Question regarding DVC commits, do you also have the notion of committers? When I'm looking at a code base with Git, I like to point fingers using stuff like git blame.
Yeah, for sure.
Do you have the same thing with DVC or not?
Yeah, so yes, because if I do something and I git push it, then I'm the author of the commit. Because DVC is, or the data versioning done by DVC is very much tied to your Git commit history, that's reflected there as well.
Anyone else wants the cube? More question? Oh, you got a question. That's an easy one.
Yeah, hi. Thanks for the talk. And is there a possibility of integrating data versioning tools with the concept of a feature store?
So this is something that we are working on. It's in progress. Right now, DVC is by and large file-based, so that's also the use case I would recommend it for. But yeah, our ecosystem of tools is ever evolving. So if you're interested in seeing that, please join our GitHub, join our Discord, and get into the discussion. Because we're very much community-driven in our development. So if we know that the need is out there, we may yet build it.
Okay, cool, thanks.
There is another question in the front row.
Are you?
I haven't actually played it yet. So I haven't also had the need to update it.
But did you see the starters? Are you picking the fire one or the water one?
Oh, yeah, okay. Fair enough. The duck does look nice.
It does.
Yeah. Oh, yeah. No, but I don't want to spoil myself straight away. It's about the exploration.
Make a Pokédex joke, please.
Any other questions?
Anyone all the way in the back to make me walk again, or?
Hey, like you said, you get more steps.
Yeah.
All right, I think we can go on a break. But before that, please, another round of applause for Rob.
Thank you.
Thank you. And I do want to know, how did you get your character made?
Commissions on Fiverr.
You had a commission done. Nice.
Feel free to post comments and questions below. Beyond our tools themselves, we have many resources for you on your ML journey. Visit our docs, our blog for tutorials, our YouTube channel, our Discord server for support and community, and our free online course. You can find all the links to these resources in the description. Thanks for making it to the end. DV and I will see you in the next video.